Okay, welcome back to decision analysis lecture notes, and we are now in chapter on decision matrices and rules and section stochastic decision rules. So we had non-stochastic decision rules in the previous video lecture. Now we have stochastic decision rules. And so this means that now the decision rule depends not only on the reward matrix R, but also on the scenario probabilities P. And the most natural stochastic rule is the so-called expected value rule. So we want to maximize the expected value. So what is the expected value? So V expected value of the alternative I is that we sum over all the possible scenarios, look at the reward Rij with the scenario J, and multiply it with the probability of the scenario and sum these up. So this is the expected value rule. And if we want to use the language of probability theory, this means the random variable, so now AI, the alternative I, is considered as a random variable, then the decision making will be used expectation. So V EV expected value of I is the expectation of AI, which is the sum of AI given Sj, probability to Sj, and remember this AI Sj is Rij, and probability of Sj is Pj. So you see that this rule indeed is this rule. And the optimal decision, so this is a maximization rule. Of course, we want to maximize the expected value. So A star will be the AI star that satisfies that the V expected value I star is the maximum over I of the expectations of AI. So consequently, the expected value rule is sometimes called maxi rule. And some small remarks. So first remark is that if the scenarios Sj are equally probable, then the expected value rule is simply the Laplace rule that we saw in the last video lecture. And then some concepts. So another remark. So the expected value rule is also called the risk neutral rule. So what is the risk neutral in this rule? So the idea is that suppose that the decision maker who follows, well, not suppose, but if a decision maker follows the expected value rule, this means that she is indifferent between the two following choices. One, certain reward, sorry about this confusion, I'm losing my face here. So a certain reward of €1 and with probability 1/2 reward of €2 and with one probability 1/2 nothing. Let me try to put it like this. No, now I'm not going to lose it. All right. And this seems reasonable, this risk neutral rule, but let us anticipate something different. So most of us are probably indifferent between these choices. One certain reward of €1 and 50/50 of €2 and nothing. And probably we would be indifferent on this game altogether. €1 here or there, who cares? But the gist of the question is in scaling. A risk-neutral decision maker is also different if we scale these rewards. A certain reward of 100,000 and with probability 1/2 a reward of 200,000 and probability 1/2 nothing. And now most of us probably are not indifferent at all. So actually most of us will probably choose the alternative one, so €100,000 for sure, and not gamble with the 50/50 chance of getting 200,000 or nothing. And in this case, if you choose 1 over 2, you are so-called risk-averse person. So this choice 1 covers the risk aversion, and choosing 2. So if you want to gamble with high amount of money, then that's called risk seeking. And now this phenomenon is something that we want to model mathematically. So we know that most people are risk averse and some are risk seeking. That's also possible. And we want to uh, extend this risk neutral rule to risk seeking and risk averse rule. And this is done by what is called utility functions. And the idea is that we still use the expected value as the decision rule, but we do not apply the rewards, but the so-called utilities, U. And these utilities are calculated from the reward matrix by using so-called utility function. So we are using uij, which is the small u, is just a fixed function, utility function of the reward rij. So what kind of utility functions are we using? So this again could be any increasing function. It has to be increasing for this to make sense, but otherwise it could be anything. Uh, so the shape of this function tells us what kind of behavior we are trying to model in the decision maker. So if the so-called marginal utility, so marginal utility is the derivative of the utility, if this is decreasing, then the decision maker is risk averse. And the same way if the marginal utility, that is the derivative of the utility function, is increasing, then the decision maker is risk seeking. And in general, it can be at some values increasing and some values decreasing, so there can be risk averse and risk seeking behavior for different scales. That's also possible. So here is just a picture showing what they look like. So this is a typical risk averse utility function. So the derivative is decreasing, and this is risk seeking utility function. So the derivative is increasing. And the rule, once the u is given, of course the problem is to finding the u, but let's just at this point assume that the decision maker knows his or her utility function. And if the utility function is given, then the value function v util of I is just you take the rewards and pass them through this utility function. So you look at the utilities and weight them with the probabilities. And in the same way, in the language of probability theory, this means that the VI util is the expected utility of AI. So the rule is expected utility. And these are just writing this expected utility in different ways. So there is nothing deep in these calculations. Here I'm just stating the same thing in different formulas. And the value of the optimal decision, so this is a maximization rule as almost all our rules are. So A star will be the AI star, the utility rule where the maximal utility is attained. And this is why the utility rule is sometimes called maxi EU rule. All right, so this is all and well if we know the utility function. The problem is that it is not always known. But before we go to that, so let me state out this expected utility rule is sometimes called the gold standard of decision making, and this follows from the remarkable results for Neumann and Morgenstern that basically show that a decision maker is rational, whatever that means. We don't go into details what does it mean that you are rational in this course, but there is a set of axioms that tells us when a person is rational or not, and it follows that you are rational if and only if you use expected utility rule with some utility function. You have freedom to choose a utility function, but you have to have some utility functions you are optimizing in order to be rational, otherwise you are irrational. All right, but now the question of finding the utility function u. And well, this is a similar problem as the degree of optimism in the Hurwitz rule. So almost no one knows their utility function. And well, there are ways of estimating them, and we propose one way or one system, and this is that we build a parameterized model for the utility U. So the utility U depends on a parameter, and once the parameter is known, then the utility function is known, and then we provide a way to estimate the parameter. So this is what happens next. So we make an assumption that the decision maker is risk averse and the absolute risk aversion is constant. So what does it mean? So this is called the CARA assumption. CARA is constant absolute risk aversion. So what is the absolute risk aversion? Absolute risk aversion is a measure on the shape on the utility function. And the measure of the shape is that you take the second derivative and divide it by the first derivative. And for technical reason, we take the minus sign. This is not important here. And we assume that this kind of functional or the utility function is constant. So this is assumption. This is just an assumption. We can test this assumption whether it's reasonable or not. Some say it's reasonable, some say it's not. For us, it's just an assumption. And what turns out that if we assume this, so this is a second order differential equation for U. And this is not a differential equations course, so I will just give you a solution. So it's possible to solve this. There are many ways of solving it. And it turns out that the solution is the following. So U of R is 1 minus e to the power minus R over R0, where this R0 is free parameter. And this parameter R0 is called risk tolerance. And once this R0 is known, then the utility function is known and we can use the expected utility rule. So how do we get this R0? Well, many ways, but there is a different indifference question that gives us the R0. So to estimate the risk tolerance, we know that it's the value of indifference for the following game. What is the amount of money, money R0 that you are indifferent with alternatives? You get nothing is one alternative, but the alternative is you get R0 with probability 1/2, but lose R0 over 2 with probability 1/2. And with this kind of choices, so you're looking at the biggest R0 that you are indifferent. So if the R0 is very small, then you get R0 with probability 1/2, but you lose only half of it with probability 1/2, so you probably will take this instead of getting nothing. But if R0 is very big, then losing R0 over half will hurt you a lot. Maybe you can't afford it or the risk, and then you choose, you get nothing. So it's obvious that the more risk averse the decision maker is, the smaller the risk tolerance R0 is. And the expected value rule is a limiting case of the CARA rule where the risk tolerance is taking the limit R0 equals infinity. That's the formally expected utility rule means that you have infinite risk tolerance. And just to look at the picture, so here you can see the CARA constant absolute risk aversion utility function with different risk tolerances R0, R0 100, so this is the blue line, so it grows quickly, R0 500, so more risk tolerance is getting more a flat line, R0 1000 yellow again is closer to the flat line or linear line, sorry, and then R0 bigger and bigger, so these lines get closer and closer to a slope, and the slope will be then the expected value rule. All right, that was all for this section. See you in the next section. Bye.